And he will talk about Zeptoforth and the non-existing chips, I think, RP2350. And he will tell us about his thoughts and whether he has some. Travis, the stage is yours.
Well, over the last month and a half, I've been working on a port of Zeptoforth to the RP2350, as mentioned. It's currently in beta 0 specifically, and it largely works except for a pesky bug that was alerted to me yesterday that if you use zeptocom.js with it, it doesn't upload data properly. Very strange, because if you use anything else to upload data, it works just fine. So don't use zeptocom.js with it at the moment. But aside from that, there's not very much exciting about the port, because basically, unless you are directly accessing the quad SPI flash and you're not using the block interface, it is essentially completely backwards compatible with RP2040 version. But it does have some neat little features that this is not something that will work on the Pico 2, but because I've got it hooked up to a Pimoroni Pico Plus 2 with PS RAM, I can do what I'm going to show you right now. Share screen. It's being okay. I'm gonna go and first upload some code to it. As you see, that's the prompt, the welcome message. Just uploading my trusty Zeptoed, which is my nice editor for Zeptoforth. I'm gonna reboot. I'm gonna upload my code so I can use the onboard, not on chip, but onboard quad SPI flash as a file system. Now, the PS RAM's chip select line is hooked up to GPIO 47 on the Pico Plus 2. So that's what we're gonna initialize it as using. And then let's fill part of the, not all, because it'll take a bit, but part of the PS RAM with data. So and then I'm going to go and write some code to verify that the PS RAM got written as it's supposed to be written. And one thing to note is in the code here, I'm writing more data than will fit in the XIP cache to ensure that the data will actually hit the PS RAM. And then if it doesn't fail, I'm just going to, as a little test, go and dump part of the PS RAM completely unnecessarily. Now I'm going to run this little program. There it goes, which it first wrote for the first 2 kilobytes of data, not the first 2 kilobytes, no, I'm bad. The first, it wrote 64K cells twice with incremented values. And then it looped through them again and compared the values in those cells with the loop variable to test whether they've been written correctly. And then it dumped out the data, which is what we get here. And this is a new feature that is available only on Zeptoforth for the RP2350. It's not available for any other version of Zeptoforth. And this PS RAM is slow because it's interfaced with over a quad SPI connection. And furthermore, it competes with the quad SPI flash for XIP cache space because they both share a single 16K XIP cache, which is SRAM. But if you want to do something that requires large quantities of space, it is ideal. Like, for example, one example of a little project I'm thinking of implementing at some point is implementing Conway's Game of Life, which I've already done in 4. But on this Pico Plus 2, it gives you 8 megabytes of PS RAM. Megabytes, which is good for a quite large life world if you devote each cell in life to a single bit. And furthermore, it's not something truly performance critical. So the fact that PS RAM is relatively slow isn't the end of the world. Other potential use cases for this are things such as frame buffers, if you can tolerate the slowness, which will impact your refresh rate. Another use case I've thought of is if when the Pico W2 comes out, if our friends at the Raspberry Pi people are nice enough to also give us a PSRAM in there as well, it would give us plenty of space for buffers for Zepto IP. But we'll have to see if the Raspberry Pi people are so nice in that department. And other than that, there isn't actually a whole lot to talk about because most of the things that are added to RP2350 are basically just small improvements. Well, there's actually big improvements, for instance, such as the fact that it has nearly double the amount of SRAM, whereas the RP2040 had 264 kilobytes of SRAM. The RP2350 has 520 kilobytes of SRAM, which is going to be really nice when the Pico W2 comes out, because on the original Pico W, to be honest, the buffers needed for Zepto IP ate up a lot of that SRAM. So the extra SRAM will be appreciated. And there are some new features that are notable, like for instance, on the RP2350, you get 3 PIO blocks, whereas the RP2040 only has 2. So you get a total of 12 state machines rather than the 8 of the 2040. One notable feature that I have yet to implement support for, partially because I don't have a means at the moment of really testing it, is something called HSTX. HSTX is basically a high bandwidth output only peripheral. And it's meant for things like driving DVI displays. And while it's not going to be in Zeptoforth 1.8.0, which is going to be the next full release, it is something that will probably some point down the pipe appear in Zeptoforth. There's other small little improvements which I did add support for, like for instance, the RP2040 has a terrible real-time clock. Terrible. For instance, you cannot specify milliseconds with it. And with the RP2350, they tore that out. They got rid of it. And they replaced it with a always on millisecond clock, which is 64-bit. And the 64-bit millisecond clock counts as long as a small amount of power is applied to the RP2350, which that small amount of power can be applied by something like a lithium coin cell. It doesn't need to be a full amount of power to, and thus it gives you actually what you like out of a real-time clock. And while it doesn't do what some real-time clocks do and provide a BCD, year, month, day, hour, minute, second type clock as some traditional RTCs do, and similar to the RP2040, it's left up to the user, which is in my case me, to implement date conversion, date and time conversions on top of the always on timer, which the date and time conversions allow things like, for instance, I was too lazy, I did not implement this. But if you really wanted to, you could even implement things such as leap seconds and stuff of that sort with it, because it's left up to the user to implement the date time conversions, which I did implement a convenient interface for turning the values to and from date human usable date times. Another improvement in the RP2350 that I support is that you get 2 timer peripherals rather than 1. So because each timer peripheral has a total of 4 alarms, which trigger interrupts, you get a total of 8 hardware timer interrupts with microsecond precision that you can use on the RP2350. And beyond that, there isn't a whole lot to talk about. Well, I will have to go and dig deeper into my USB issues because, frankly, the Raspberry Pi people said that aside from a couple little details which I'm following, it should be essentially source compatible, and it clearly isn't. So I'll have to dig into that deeper. And one word to the wise, though, if you're going to run it out and get an RP2350 board, is that if you've been paying attention, there's a notorious silicon bug in the RP2350. The silicon bug affects the GPIO pads, where basically, if you've got them set to input, you got the input enabled on the pad, and you get a high voltage come in, it'll stay high at about 2.2, 2.3 volts until something pulls it down. So, and the built-in internal pull downs don't pull it down enough. So you will need to use if you want pull down functionality, you will need to use an external pull down resistor. I've heard things along the lines of 10K will work. 10K ohms for your pull down resistor should be sufficient. And also this does affect floating as well, which with floating it's even worse because you don't want to pull down. This is word to wise. So if you're using an application where you're going to need to use floating inputs, and mind you, this is different from ADC because you don't have to input enabled to use ADC necessarily. You might want to wait until they do a respec. But for most purposes, like if you're using UART, SPI, ITC, not ITC, I2C, and all those, you shouldn't have a problem. Or if you're using pull-ups, or if you're willing to devote a little more of your BOM to pull down resistors, you shouldn't have a problem. But that's just something to keep in mind. So do any of you have any questions?
Yeah, I have a question. Travis, do you actually have chips apart from the beta chips that you might got for developing? But are there other chips available actually?
Last time I checked, the Raspberry Pi people were only providing chips to their selected board vendors. So if you honestly, if you want a chip, not a board, but a chip, you'll probably have to buy aborted with the chip off of it.
Yeah.
Yeah. Did you consider running this Zeptoforth on the RISC-V course rather than the Cortex course?
No, there's a reason why. It's because Zeptoforth is written in ARM Cortex-M assembly. And
So
targeting the RISC-V cores would essentially require a complete rewrite of its kernel. And while I have considered writing a rewrite of Zeptoforth for RISC-V, the matter is that basically on the RP2350, there is no real advantage to using the RISC-V.
And do you support floating point, the new hardware floating point that the new Cortex provides?
At the moment, no. That's probably something that will come in a future version of Zeptoforth, but at the moment, I only support integer and fixed point.
Okay. Understood.
Travis, which modules are you using? Are you using the Pomerone Pico Plus 2s?
I've been using two different boards, the Pico 2 and the Pomerone Pico Plus 2. Mind you that the PS RAM is not available on the Pico 2. Any more questions?
I'm just happy that you're finding all the bugs before the rest of us do, Travis.
Yeah.
I really hope that this USB issue I've been running into is just a stupid bug in my code, because we don't need more silicon bugs. To be honest, I found while I was developing this something that appears to be another silicon bug, a minor one that's easy to work around, but a silicon bug nonetheless. That what it was that if you went in, there's a register in Bemann timer called run, which in the refman, or the data sheet as the Raspberry Pi people call it, if you set this bit, it will cause the always on timer to count up from its current value. But what I discovered was that it did not have that behavior. Rather, the behavior that it has is that if you set the bit, it will cause it to count up to from the last time it was set to. For instance, let's say after I booted my board, half an hour ago, or let's say I set it at 10 o'clock to 10 a.m. 2004-09-14. And then I cleared the bits, and then I set the bit again. It would set the time back to 10 o'clock. Whereas according to the refman, it should just resume counting up from the last place that it was at. So that feels to me like a bug, and I mentioned it on the Raspberry Pi board forum. But because companies really prefer not to go and fix things when they do respins, and because this has an obvious workaround, which is don't touch the run bit. I feel like they probably just won't fix this.
Yeah, probably be an editor and a voice note in the documentation.
Well, I would have appreciated it if they had made an errata about it, but they didn't.
All right. Yeah. Are there any additional questions to Travis? Kat, do you have any additional questions?
I think Kat has a question.
Yeah, it just ordered empty boxes, 800 empty boxes, cardboard. No. Yeah. So yeah, Travis, thank you very much for the heads up, and let us know if you find any other things regarding that chip. You know, your work is very appreciated. Right. So having a look at the schedule, we will have a short break.